So, hello everyone, and this is welcome to Paper Money, your own channel. And this is a quantum mechanics lecture by Biplab Datta. This is the 25th lecture. All right, so let's start. Now, I'll be continuing with the discussion we started in the previous lecture. All right, so the we had discussed one case for the step potential, and I'll take it further with discussing the case where the energy of the particle is less than the potential. All right. So I hope you remember things from past lectures. Okay. Because I will be continuing with that thing only. All right. So if we have this potential, let's draw this again and write it down here that we have this thing, step potential. We are continuing the discussion. Step potential. All right. So what we have is this is also continued from previous lecture. Continued from previous lecture. All right. Now, what is happening here is that we'll be discussing this case, K, which is case 2. Case 2, E is less than the energy, total energy of the particle is less than the potential, the barrier potential, not the barrier, the step potential. All right. So let's draw the diagram and see how does it look. And this is the V axis and this is the X axis. All right.
Good morning, sir.
Good morning. So we have this, say the potential is at this side. The potential is at this side. Okay, on this it is 0. There is the potential which we have here. Now this is Vx. Okay, the motion is in 1D. Purely the particle is traveling along X direction on the X direction, but this energy is being stored for at this level on this axis. Okay, now this is the region 1. So this is region 1. This is region 2. All right, as we had already marked previously. Now, if say the particle, now let me bring down this I a little bit lower so that I can fit in the energy. So let's say that the energy of the particle is moving like this. The particle is moving here. All right, particle is moving along this axis. The energy of this particle is represented on this level. Say the total energy is E. Okay, and this is a V naught. All right. Now we see that the energy of the particle, which is the the particle in the beam, they have energy less than the V naught. All right. So let's see what happens. What does mathematics gives us? What does quantum mechanics gives us? All right. So in this case, this is the difference here. The difference in this level, this energy is purely kinetic energy. All right. There's no potential energy because v is 0 here. All right, in this region. So this is x equal to 0. All right. So the potential in this case, we know this definition that we had already defined it. I'll write it again. This is 0 for x less than 0, and this is v naught for x greater than equal to 0. All right. So this is what we have here, and if we try to see what is happening now, one thing we are sure about is this region. You can say that this region is what, classically allowed or classically forbidden. This region is classically allowed, right? This x less than 0 region is classically allowed for this particle with this energy, which is positive, and it is allowed completely. But in this region, this is classically forbidden. All right. So you can say, let's write it here now. Classically, for this particle energy only. All right, we are not talking about the previous case. In that case, all the regions were classically allowed, but in this case, since the energy is less than the V naught, the classical this region, the region 2, is classically forbidden. All right, now we know what happens in the classically forbidden region. the kinetic energy turns out to be negative. Okay, theoretically. Okay, we do not define it to be negative anywhere, but it turns out to be negative in this case. All right, and in this one, in this region is classically allowed. The particle is free to move. Okay, classically allowed, and the kinetic energy is of course positive. All right, so Ke is positive or equal. It couldn't be zero also. Doesn't mind, but doesn't matter. But in this case, we have the kinetic energy is greater than zero. All right. So let's start the calculation. Now, what the like this is everything boils down to one thing, which is the Schrodinger equation. Okay, we'll start with that. So in region one, what we have is, now I'll just abbreviate this term, which is time independent Schrodinger equation. Okay, so time independent Schrodinger equation. Schrodinger equation. All right, so I'll write it as from now onwards TISE. All right, so we'll write this down, the Schrodinger equation in region which is defined by x less than 0. All right, so let's see how does it look and how does it work out. Now if we put down the Schrodinger equation, this is minus h cut square 2m. Now you already know how to like already know this thing, what to do, how to write the Schrodinger equation. Now v is 0, potential is 0, so we get rid of the potential term. What we are left with is this. Okay, so we have this in this region, vx is equal to 0. So we have this relationship. Now if we just rearrange, all right, what we'll get? We'll get this thing, and which is the same as the in earlier calculations. All right, now and k is given by root uh, 2me by, this is root 2me by h cut square. All right, so this is the wave number of the particles de Broglie wave in the region 1. All right, so we know the solution already, okay, of this form, the equation, so which is a to power I kx plus b e to power minus I kx. All right, so and this is in the region x less than 0. All right, now we'll use another one term. We'll learn just start referring to these kind of solutions in the classically allowed region. Now this is, we term it as oscillatory. Okay, we term this solution as oscillatory. Okay, this solution of the wave function, the form of the wave function is oscillatory. Okay, now this kind of behavior comes in regions where the region in the region which is classically allowed for the particle. Just a name given to it. Okay, because the wave function is the wave is completely formed, it's not decaying, it's not exponentially increasing. Okay, it's oscillates. All right, if you see the real part, of these wave equation, you see there's oscillatory wave form. Okay, like sine or cos, real or imaginary part separately. All right, so we call this term oscillatory. So this is a way to talk about it, that if somebody asks you what is the form of the, like, is it oscillatory or decaying in the classically allowed region. So always remember this, that whenever you have this format, when you have e to the power iota kx or plus b e to the power minus iota kx, these represents oscillatory solutions. Okay, why oscillatory? Because if you just plot the so you cannot plot this in a 2D graph. Okay, so you can plot this separately, this thing, your sine part and the imaginary part and the real part separately. You can see that of course the sine is oscillatory and cos is also oscillatory, so that's why the name. All right, so now next is in the region, let's talk about in region 2. All right, So in this case, the time independent Schrodinger equation, okay, let's write it down in region x greater than 0. So minus h cut square by 2m, and this is the wave function psi 2, okay, derivative with respect to x, in fact double derivative with respect to x. Now the potential here is not 0, which is v naught equal to e psi 2. Okay, now in this case, derivative with respect to this thing is now let's rearrange. Now in this case we are defining we are making the arrangement such that, because see the v in this region, what is happening in this region, v naught is greater than e. All right, so we are defining a quantity now, so it will rearrange the quantity in such a way that this we define a quantity here, that is gamma, all right, which is this term, all right, and this we define it to be positive in this region, okay, which is because v naught is greater than e. Now in this case the gamma is a positive quantity. All right, gamma is a positive quantity. We rearrange the equation in such a way. Now let's solve this equation. What do we get? All right, this is equal to gamma, this is equal to gamma square psi 2. All right, so now this equation is, the solution will be this, gamma x plus d minus gamma x. All right, so I hope you have you understand how you get these solutions, okay, from differential equations. Or if you don't remember, you can just look up once how to get the solutions for these kind of equations. Okay, I will not get into that part. Okay, now what to talk, like in the previous case we had got rid of, this one term was there which we got rid of. Okay, in this case also there is the argument is different here. Argument is that if we put, now we want the wave function, we want the wave function to be finite everywhere. Okay, we want the wave function to be finite everywhere. Now the oscillatory function which we got, it is finite everywhere, all right, in its region. Now in this case, this one, the now gamma is a positive number. Now there is no iota here, so there is not oscillatory. Okay, so there is an exponentially increasing part, there is an exponentially decaying part. All right, so what we have is if we put x tending to infinity, so what we get psi 2 becomes infinite, right? Because one of the term is exponentially increasing, all right, and it will dominate. Now to make psi 2 acceptable, to make psi 2 acceptable, psi 2 acceptable, we must have c equal to 0. We must have c equal to 0. Okay, because we need to get rid of this term, this exponentially increasing term, to make it physically acceptable. All right, so we have now the final so that means we have to put c equal to 0, which means this the psi 2 is equal to d this is minus gamma x. All right, and this is the wave function which is in the region, and this is the acceptable wave function which is in the region x greater than 0. Okay, now this solution, when we talk about this solution, now this solution is called, we'll term it as decaying. Okay, this solution is, we call it decaying. Now this decaying part appears whenever we have a this decaying solution appears whenever we have a classically forbidden region. Classically forbidden region. Okay. Now we can see one thing, that for classical step potential, there was no chance, if the energy of the particle is less than the step potential, to for the particle to pass the barrier. It will always be reflected. But in this case, we see that there is a finite problem. If we just take the mod square of psi2, we'll see that the probability is there. There is very small probability, but the probability is there. Okay. It's non-zero. Okay, so there are chances of finding the particle. Now, how to imagine about how to think about it? It's very difficult to like imagine things like that. What does the particle do in the inside the barrier? What is the energy of the particle? Kinetic energy of what happens to the kinetic energy of the barrier particle in the barrier? Now, these questions are very difficult to answer. Okay, and the experiments which have been conducted, there have been no experiments, as far as I know, as far as I could find, which had studied the behavior of the particles inside the barrier. All right, so this is still you can say a mystery. Okay. So to what happens to there are quantum tunneling gadget, like there is scanning tunneling microscope, there is the tunneling transistors. Okay, the applications are there, but what is happening to the particle inside the barrier, it's a kind of a mystery. And in my project in my IIT Kanpur, I did this project that we had to measure. One of my prof gave me that if you have a scanning tunneling microscope, we'll discuss about the tunneling barrier. If you have a tunneling microscope, what is the time the particle spends in the barrier? Okay, we had to calculate that, and that was like 10 years back. Okay, so in that case, I was able to figure, like just give a hypothetical experimental setup, that how can we do it, okay, using lasers and the STM. But it was still an open problem then, and still a problem. There are lots of research going on in that area. Okay, still it's an open problem. Okay, but with the with the advent of after this, like attosecond lasers have come out after the invention of the attosecond lasers. Means the pulse width is like the time is like in the order of 10 to the minus 18 seconds. Okay, so using those equipments, it is possible to have some measurement of the time spent by the particle inside the barrier. Now, in this case, the particle is not coming out other to the other side of the barrier, because the barrier here we have taken is infinite width. All right. So lots of discussions can be done on this area. So it's a matter of research. All right. So we'll stick to what we already know mathematically. All right. So we need to find out now. Now everything comes down to one thing, which is we want to calculate what are the current densities, probability current densities. Okay, and we'll then see what is the reflection coefficient and the transmission coefficient. All right. So in this case, we have three coefficients to be found out, which is this A, B, D. So finally, what we need to do is we need to find out B and D in terms of A. All right. So where do we go? We go to the boundary conditions. All right. So boundary conditions comes to our rescue whenever we try to find out the coefficient. Okay. So go to the boundary conditions, and let's see what we get from there. All right. So what we have here is this is psi1 x is equal to. So see, I am not aware of what is exactly going on. Last year I did this thing. Last year I again searched for this this topic, that how much time is being spent by the particle inside the barrier, how to find out experimentally or even predict it theoretically. So there are many papers on it. Okay, I did a literature survey last year also, because when I was teaching this course to people in from chemistry, like quantum chemistry, they had one question which could be which asked about the time spent by the particle inside the barrier. Okay, where it could be derived using the uncertainty principle, but it's very crude, like it's not exact. All right, it's very far from the exact thing. so that led me to go into research again, like look up the papers and literature what is available at the time. And then that was the last thing. So I did it last year. Okay, more than, it has been like more than one year. So I do not know what has happened in the last year. Okay, so if you are interested, you can look it up, but don't do it right now. Okay, so the boundary conditions here is psi2. All right. So now this, I'm telling this because the video here is going to be there in YouTube till the account is there. All right. So I don't want anyone to say that, okay, you said this has already happened. So I do not know what is happening right now. Okay. So let's stick to whatever is available in this textbook.
मतलब सर क्वांटम केमिस्ट्री में अवेलेबल है इसका
नहीं
एक्चुअल
नहीं,
रीजन?
see, you're getting everything wrong. Quantum chemistry mein, I taught in quantum chemistry, I taught the students. There was a question from TFR chemistry. Okay, which asked you to find out the time spent by the this thing, the particle inside the barrier. So we can do it approximate, not approximately, it's far from approximate. We can have an empirical derivation using the uncertainty principle. Okay, I'm not saying it's available in quantum chemistry, it's not available anywhere. I'm saying that was a question put up by, I don't know, there's a TFR chemistry people. Okay, so please don't come to conclusions like that. Okay, I'm not saying it's available in anywhere. I'm saying that it's a area of active research. Okay.
Oh, okay sir.
Yeah, and we can of course derive it now also using this uncertainty principle, empirical derivation. It is not exact. Okay. So now let's label this. Now this is already 1, so let's label it something else. So this is 1, and the other boundary condition which we have is so the first derivative, the wave function should be continuous at the boundaries. That is fine. And then if we put x equal to 0, we get this relationship. Now you know how to do it. Okay, I'm just stating the thing. If you put 0 on both sides of this thing, okay, after putting x equal to 0 on these two equations, psi1 and psi2, you'll get this relationship. Okay. Now, if the first derivative should also be continuous, because the potential here is finite, and we know that for a finite potential, this momentum should be continuous, and for the momentum to be continuous, since the momentum has an operator form of iota, this thing, iota h cut derivative with respect to x. So the first derivative should also be continuous. Okay, so which is x equal to 0. All right. Now, if we just, I'm just writing around the solution. What you'll get is this one. All right, you'll get this minus d. Now what we have here is, we can instead, we can rearrange this thing. We can rearrange this, and we can write like this: minus gamma ik d. All right, so we can write it to be this. All right, so now what we can do is, we can using now by 1 plus 2, like if we add 1 and 2, okay, so we can write 2a is equal to, this is d. Now what do we have here is, if we add them, so we'll get 1 plus iota gamma. And now here what we are doing is, we are multiplying iota above and below, and we'll get this result. So we can have a plus sign here. Okay, now this looks good. So we'll have this format. Okay, and we can write d in terms of a. So d by a is equal to 2k divided by k plus iota gamma. All right. Now we have this equation. Now let's call it. So okay, so this was 2. So this was, let's make it 3. All right. So we have the relationship between A and D. Now let's talk about getting the relationship between A and B. Okay, so using one, if you use one and just place instead of D, you can use this thing. The using three in one. Okay, so this is one. Now what we have is A plus B is equal to, now instead of D we are writing K plus iota gamma. Okay, A. Now this is equal to B equal to 2K by K plus iota gamma minus 1 A. Okay, so we can rearrange this and we can write as minus iota gamma plus K divided by iota gamma plus K. So we have the relationship between A and B. All right. So what do we have here? We have, let's label it 4. So we have the relationship between A and B, A and D. Okay. Now we are interested in these two things, and the experiments as well in theory. So this is what we measure in the experiments. So reflection coefficient. Okay. Reflection coefficient is given by R. This is we know that it's a ratio between the modulus of JR and JI, incident current density, and this is the reflected current density by incident current density. So this gives you, now we can of course write it like this. Okay, we can write like this also. Now this will be, if you see this, if you see this thing, if you take the mod of this quantity, what will you get? You will get 1, right? If you take this mod, so what you have, if you take the mod here, so this will be gamma square plus k square. This will be gamma square plus k square. Okay, both will be gamma square by k square, so you'll get 1. All right. Now you can also see this thing, you can also do this thing by this method. You can write like this, that b star b. Okay, so in this case, if you write down this thing in terms of A, what can you write? You can write 1 k minus iota gamma plus k plus iota gamma. All right. Now this will be square conjugate. This is k minus iota gamma plus k plus iota gamma. All right. So you have, and we have a this a mod a square. Okay, we are using this relation using 4. Now what we have used is using 4. Using 4, we are writing this thing, and what we get is this. Now if we if we just do this calculation, what do we get? We can see, if you take the conjugate, this will become plus, this will become minus. Now each of them cancel each other, so the mod square of b, the b mod square is equal to a mod square, which is also giving you 1. All right. So yeah, so the reflection, all the particles will be reflected back, but the quantum mechanically what happens is it says that there is finite probability of finding the particle in the forbidden region. Although the particle will return from the barrier, but it will penetrate into the barrier to some extent. Okay, the step potential, not the barrier actually. But when I say barrier in this case, it's a step potential. Okay, the barrier is defined differently because the particle can cross the barrier. Okay. Now in this case, what we have is JT by J incident. All right. Now if you try to get this thing, if you try to calculate this value JT is the probability current density of the transmitted wave. Okay, so if you see the J value which we had calculated, the form of the J, that in that case there was quantity inside the bracket. Okay, which was, if you remember the form, okay, this was the form, right? Now we had written down this format. So in this case, if you see, let's take this to the other, like let's copy this thing and take it to our current page. All right. So if I try to calculate this thing, okay, J for the transmitted wave. Okay, if I want to calculate the J from the transmitted wave, so what do we get? Now the transmitted wave is real. Transmitted wave is real. All right. So if I put psi2 here, now if I want to calculate JT, now this is psi2 here, this is psi2 here. Okay, this is psi2 here. And if I want to calculate this, so we know that psi2 is real. Okay, psi2 is real. So what happens to this? These two terms become same. Okay, these two terms, these are same, right? This is same as this term. Okay, both the terms become same, which means that we have a zero answer. Okay, we have a zero answer. Now these two are same because psi2 is real. Okay, this implies this, and this implies this. So this becomes zero. So for always remember that for a this thing, the real wave function, the probability current density is zero. Okay. Now what happens here is you can think of it as if the number of particles passing through this, like entering the barrier, is also the not the barrier, the step potential is also the number of particles which are coming out of it. Okay, the particle travels to some point. Okay, you cannot think of a particle; it's like a wave actually. Okay, it's better to think of a wave. So wave penetrates to some extent, and then again it comes back. All right, so the flux remains zero. Okay, the flux of particles. So in this case, now let's talk about the penetration depth. Penetration depth. All right. So how far the particle penetrates. All right. Now this is only defined. This is only defined for. This is defined for E when the energy of the particle is less than V naught. Okay. It's not defined for the other case because in that case the free particle is free to move everywhere. All right. So it is defined as. It is defined as the distance at which the wave function reduces to 1 by E of the value of the wave function. All right, of the wave function at the barrier. Now I do not know if you have come across this. You must have come across this kind of quantity in electromagnetic theory. All right, regarding the skin depth. Whenever a electromagnetic wave is incident on an interface or conducting interface, okay, so there's a quantity called skin, so in skin depth. Okay, so this is also defined. The definition is similar. Okay, so in this case we add the, now this is the value of the wave function at the barrier. Okay, which is x is equal to 0. The barrier is at x equal to 0. All right. So this is how defined. It is defined as a distance at which the wave function, whatever the wave function value is, it reduces to 1e of the value of the wave function at the barrier. Okay, let's see what it mathematically looks like. So what we have here is psi. We know that psi2 is equal to d e to power minus gamma x. All right, which is x greater than 0. All right, we have this solution in this region. Now psi2, if I take these things, the definition, the way it's defined, if we take the value at x equal to 0, okay, so let's take it to this way. Now if you put x equal to 0, what will you get? You will get d. All right, now it says that the value of the wave function becomes 1 by e. okay, at some distance. Okay, so let's see now what is the value of this. Let's say that x naught, let's say x naught is penetration depth. X naught is penetration depth. Okay, let's say that x naught is penetration depth. Now in this case we can write d equal d into gamma x naught. Okay, now this is what you have here. Now from the definition we can write like this, that this is 1 by e of psi 2 at x equal to 0 is equal to psi 2 at x equal to x naught, the penetration depth. This is the definition of penetration depth, right? It becomes 1 by e of the wave function value at x equal to 0. So let's see what happens. What is the value of x naught? So if we write down the forms of the wave function at respective values of x, so we have this relationship. Now what we can have is this e, now d cancels out on both sides, so we have exponential inverse and we have minus gamma x naught. Okay, this is not exponent, this is the Euler number. Okay, now what we have here is what we can write, we can compare this thing, we can compare. Now what we have is we can write gamma x naught is equal to 1. All right, which implies that x naught is equal to 1 by gamma. Okay, so x naught is equal to 1 by gamma is equal to root over h cot square by 2m v naught minus e. All right, so this is what we have now for relationship for between. Now this is the penetration depth what we have from the calculations. Okay, so one thing you can see that if v becomes infinite, which was the case we discussed in 1D potential, if the potential is infinite, okay, instead of being finite, so what can we say about x naught? X naught will tend to 0. All right, so this is what we are getting, right? There was, the particle was not able to go outside, right? It was not able to go outside the barrier in 1D. Like this is a case of 1D potential, 1D infinite potential, 1D infinite potential. We had already assumed this thing. Now we can prove it from this point of view. Okay, we had assumed that the particle cannot go outside because the potential is infinite outside. Now we can see this thing happening here, that the penetration depth becomes 0. The particle cannot enter that region. All right, if you have an infinite potential. Now let's look at the diagrams which we can draw for this thing. Okay, so let's draw the potential here. Now I'll just take up this potential again and just copy and paste it. Okay, so I'll take this drawing and just use it. All right. I'll use it here. Now in this case, let's get rid of these things. Okay, so now let this be there, and I'll remove this part. Okay, I'll write it somewhere else. So this is the region what we have here is, this is the energy. Now the wave moves like this. The wave is like, I'll try to draw it as correctly as possible. So the wave is oscillatory here. It oscillates like this. Okay, now when it reaches this region, now it decays in this region. Okay, it decays to 0. And this is the for incident wave. This is the incident wave. Okay, incident wave, which is oscillatory. Now we are just looking at one of the real part or the imaginary part, whatever it is, separately plotted. Now this is basically the wave, which is a e to power minus iota kx. Oh, sorry, not a minus, plus iota kx. Okay. and then we have the reflected wave. Okay, now both have same magnitude here. Okay, both have same magnitude here, and but the directions are opposite. So this is the region 1. Okay, region 1, and this is region 2, region 2. All right, so now we have, let's draw this thing. Now both are in phase. Okay, there's a phase is same. So we have this reflected wave like this. Okay, now this is not drawn to scale, so don't worry about it. And this one is a reflected wave. Reflected wave, and the phase does not change here. The phase is same because the phase of A and B are same. Okay, phase do not change. Okay, so it will be in phase, and there's a decaying region here. Okay, it decays. So this part is the decaying part, which is this is d e to power minus gamma x. All right, so this is the decaying part, and this is the oscillatory part. Now this one, this wave, we can write like this. This is b. Can we fit in here? Okay, let me write it here. So this is b e to power minus iota kx. And right, and this region, the wave function is this. Now this is a classically forbidden region, and this region is classically allowed. Now this region is classically allowed region. Classically allowed. Now remember this, that in classically allowed region, the wave function will be oscillatory. Okay, classically allowed. All right, region. Now this is the diagram here, which we concludes everything. Now we can look up a diagram for. So have you
Sir,
drawn this diagram?
hello, sir.
Yes.
Yes, sir.
Sir, since the flux is coming out to be zero, sir, so shouldn't there be also a wave going in backward direction in region 2?
No. The thing is, if you see the thing, we cannot. We are using the mathematics to find out what is happening here. So if you see the mathematics here, now what we see here, that is a like a bit of it's difficult to understand what is going on inside that. So I told you this, that why we are getting rid of this, the reflected, there is no reflected wave, there is no incident, there is incident wave, there's just the wave function. Okay, there's like where the form of the wave function is not as in the free particle case, which we have in region 1. Okay, so if you see this wave function, we have two parts, which is exponentially decaying and which is exponentially increasing, right? And
Sir,
this was put to, one of the parts was put, the exponentially increasing part was put to 0 because it was not giving us acceptable wave function if we put x equal to x tending to infinity. All right, so that is why we got rid of this thing. We didn't get rid of this, that there is no reflected, the earlier argument which we had in the region, this e greater than v naught case. In that case, there was no incident particle from the right side to left side. Okay, that was the argument there, but here we are not talking about that.
sir,
Talking about the form of the wave function which we are getting in this region.
sir, I'm getting this argument that why we took c equal to 0. From this perspective, I'm understanding why the wave function should be like this. But my confusion is like, see, we have mod psi 2 square is not equal to 0, so the wave should penetrate. But then we have flux equal to 0, so how will the flux become 0? Because the wave is exponentially decaying and dying out.
Mhm. So it's not, see, that is the that is where we fail to imagine things. I told you this, the whole the story about the presence of particle inside the barrier. Okay, it's very difficult to comprehend this thing. All right, that even impossible to comprehend what is happening inside. So this is the results which we are getting from here, is that it looks like the particle is now we cannot imagine that the particle it's like a wave thing. Okay, the probability is finite, but what is doing, it is moving forward, backward, we do not know anything about it. the dynamics of the particle inside the barrier is not known, if you get my point.
Yes, sir, I got it. So can I ask something?
Yes.
So like when we have a wave function like psi is equal to a e raised power ikx plus b e raised power minus ikx. So we say that the exponential positive part represents the wave going in positive x direction, and exponential negative part shows the wave going in negative x direction. Sir, we can't say that here na, like when we have psi 2 is equal to c e raised power gamma x plus d e raised power
No, no,
minus
no, no, no. We cannot talk about a wave moving forward or backward.
okay, so okay.
Okay. So the dynamics of the particle is not known inside the barrier. All right. What is happening now? We are getting it to be zero. So it's okay. It's difficult to like comprehend this thing classically, because we are used to the classical things. So let's draw the graph for the different cases of the reflection coefficients and the transmission coefficients. So these are the graphs. So this is a reflection coefficient. I'm talking about R here, and this is R. This is R, and this is the energy axis. Okay, so in this region, we are taking that this is energy, increasing energy. All right, so this is E equal to V naught, and E less than V naught. All right. So it's decaying here. All right. Now in this case, this region is E greater than V naught. All right, and this reduces to zero if we keep on increasing the energy. And when E is very, very greater than V naught, this coefficient becomes zero. The reflection becomes zero, negligible. Okay, so we had done this analysis previously also. All right, and if we see that in VE less than V naught, in this region it is one. Okay, it is one, and this graph is somewhat crooked here, but it's a smooth curve. Okay, it's not like that the way I've drawn. Okay, it's a smooth curve, so it goes like this thing. Okay, so we have this the curve is a bit more smoother than what I have drawn. Okay, so in this case we can see the different cases of R. Okay, first it's completely one. Okay, for E less than V naught, and then we have E is equal to this thing this E at E equal to V naught, we have this value. It's fine. Then it when you keep on increasing the V naught, so the reflection coefficients keep on decreasing, and it goes to zero when we take E is very, very greater than V naught. All right. Similarly, if we take the transmission coefficient, we take the transmission coefficient, so and to continue with the previous question, which was asked now, that why the this thing the probability current density becomes zero. But see, the thing is, I already told this that the dynamics of the particle is unknown inside this barrier. We can just talk about the probability of finding the particle. Okay, we do not know how the motion is occurring. When I say the dynamics of the particle means how the motion is occurring, we cannot talk about it right now. All right. So it depends on what is the progress made in the scientific community. We have to check out the papers and see for ourselves what is happening right now. Okay. So only one thing we can talk about is, yeah, the particle, the probability is there. Okay, it's not like the string theory what Brian Greene shows on Discovery Channel, that he is able to penetrate the wall. It's not like that, and he appears on the other side of the wall. All right. that is fine, but what is happening in between, it's not known, right? And to imagine the thing in your head like a particle going through, it's not a particle anymore. Like it is in its own state. Okay, it is actually behaving like a wave. That is why it's able to get into the other side, even though its energy is not as much as it is required to be on the other side. Okay. Now, E less than V naught. This is E equal to V naught. All right. And in this region, you have E greater than V naught. And for, okay, let me put it somewhere else. E greater than V naught. And this is E. In this region, this is E very, very greater than V naught. So for very, very greater than V naught, the transmission coefficient becomes 1. It reaches 1. The energy is increasing this way. Okay, it is increasing this way. So now we'll not start with the other topic because it is a rectangular barrier which we'll be discussing next. So any other questions you would like to discuss? Because it's a completely full of, this topic is full of derivations, and the questions are based on this these things. So once we once we have understood how to solve the wave function in each of the region, we'll not solve it again for the rectangular barrier. We'll just write down what is the solution in the classically allowed region, what is the solution in the classically forbidden region, what is the solution in this classically allowed region. Okay, directly we know how to solve it right now. Okay, so I'll if you have any questions, then go ahead, or we can go ahead with the next session. All right.
So can I ask something?
Yes, please.
Sir, what is the quantum fluctuation?
Quantum fluctuations, I have no idea about. Okay, it's also it's a I do not know what it is. Okay.
Okay.
So my suggestion is the thing is you need to learn a lot of mathematics before you'll be able to have an intuition of what quantum does. All right. So this is just the beginning. Don't try to speculate things at your level, because you have not much information about what is happening out there. All right. So my suggestion is learn the basics first, learn whatever it's there in the textbook. Okay, and then slowly you'll build an understanding of what is happening in the current world. Okay, so don't try to pick on interesting this flashy terms like quantum fluctuations, quantum dots, okay, and whatnot. All right, so don't get into those things right now, because just talking about it in words doesn't make any sense unless you have a good concrete mathematical background. Okay, so first build on that, and then you can understand things better. All right, you'll understand this whatever I'm saying once you enter your masters. You'll understand this things better, and then you go for PhD, then you'll understand my words. Maybe these words are not making sense right now, but you'll understand it when if you continue to do physics for next 3-4 years. All right, so thank you for watching. Have a great day. All right.
Thank you, sir.
All right, so there's a session at 8, okay, and that will not be uploaded to YouTube. All right, so I hope you can just attend that lecture and make whatever questions you have, okay, in mind. You can ask there. All right.
Okay, sir.
Okay.
Okay.
Thank you so much. Have a great day.
Thank you, sir.
Thank you, sir.